Yeah, welcome again to the next session. We are now having here the AMZ Zurich driverless team, so I would like to introduce them and give them a warm welcome for their presentation of a successful FSD participation.
I think I will use this one, if you don't mind. So thank you very much. It's always a pleasure and an honor to explain our approach here. Today I'm presenting with Rafael and Manish. Rafael worked in the 2017 car of AMZ Electric, and is doing the project lead for the new season of AMZ Driverless. And Manish worked in the state estimation of AMZ Driverless last season, and he's working on the simulator this season. They will introduce the hardware actuators on the car, and Manish will introduce the whole software stack. I know that's what you are most interested in, but before I will do a bit of an introduction of how our season went and what things that we failed dramatically and some things that we actually managed to do okay, because I always think we can learn from these things. So I would like to start with a quick video. So of course that's what we achieved after season, in post-season, that never happened before Germany. I would like to start a bit with two quotes that when they told me that I had to do this, I was thinking about. I think Formula Student is designed to take everyone to the limit, and it's designed by engineers, so it actually works. I also think if we knew or if we thought that giving up was actually an option, we would have thought about it 2 or 3 times throughout the season. We had really rough moments, but I'm not telling this to disencourage you, but just to tell you that what you are going to start now, it's actually a really rough challenge. You will have very bad times, but if you don't give up and you keep fighting until the end, it will for sure pay off. Doesn't matter if you win or not, you will learn a lot, and it's a very interesting experience. I'm going to start a bit in a chronological order, so how everything happened. We started last season, it was October, and we, for different reasons, didn't have a team lead. We didn't have a team. Rumors were starting, like maybe we could not assemble like enough people to do AMZ driverless this year. And we really couldn't find anyone. Like the team from the previous year was in all different countries. We had one in the UK, 3 in Singapore, 1 in Australia, and stuff like that. But at the end, we found someone. It was a very different profile from what AMZ driverless or AMZ used to have. So she was not an engineer. She had never been in AMZ before, and she was a girl, right? So we started a completely different approach. And then once they told me that they found someone to do the team lead, I also joined to do the technical lead and see what we can do. We didn't have anyone, or we had one person from Gotthard, which is the car that we used. And he said very clearly that he didn't want to do hardware. So everything looked like a challenge, like everything was upside down, but I remember like 2017 team from Kids, from Karlsruhe, always saying that they almost didn't have anyone for the car or anyone for hardware, and they still tried, and they fought very hard, and they were 2nd overall. So there was no excuse for us not to try, you know? So at least we had to fight, and then we'll see what we can do. So we assembled the team lead, and then we move on. The first thing we need is actually a team. So we move on to recruiting. We thought a lot about what we wanted. We wanted people with project experience, you know, that they were team players, that they were willing to take responsibility. And if you ask me now, I would want people that are willing to commit. That's the only thing that is needed. We had a lot of problems throughout Gotthard year, and the only reason why it worked is because people were willing to do whatever it took. Like, we told them from the beginning, everyone you see in this room is the team. Any problem we have, we're gonna have to find the people and the manpower here. Because at the beginning, we always had this thought of, oh, we can ask people from Gotthard to fix it. And then soon we realized that that doesn't work. So if you have a team of committed people, that's the best thing you can actually have. Very different structure to AMZ Electric. We are 18 full-time members, or full-time starting from like Christmas or something at least. We are all master students from very different backgrounds. So robotics, electrical, mechanical, computer science. We are 10 different nationalities. So of course, there are some rough moments and sometimes that it's difficult to understand each other. But it's also a lot of fun, right? So in the same night, you can have Italian dinner with Indian dessert and some German beers. So I think it was very exciting. Also, there are 4 girls in this team, which is an absolute record for AMZ ever. And I think, of course, it's still very little, but it's something to be proud that they are engaging in driverless, more in computer scientists, and even more, almost every team in Germany or in Italy had a girl in the dynamics team. So they have relevant roles, and it's very cool, and I think this is something to be proud of. One more thing about the team, I think as a team lead member, that's your most valuable asset or your only asset. So you actually have to take care of them. You have to admire them. You have to respect them, right? And part of that sometimes it's very hard because we were in exam period and we always thought, okay, with all the FSG in our exams at ETH, it's very hard that they take credits on the second semester, but at least we'll leave the first semester exam period off. And we were late with deadlines and we were behind in many ways, but you cannot abuse them so early. They cannot burn out, you know? That those are the people that are gonna do the car and save the car and do everything. So you also have to like take care of them and then they will take care of the car at some point. After everything we learned in 2017, 2018 team didn't know anything, with all my respect, but people weren't trained. And as I said before, most of the team were outside. So we organized some kind of workshops. Everyone had their tiny bit of expertise. Some people knew Git or ROS, and then everyone had to learn all these tools so that we could speak a common language, and we can come up to the same pace, and then we can all start coding at the same level. But we also have computer scientists and electronic people, so they need to understand the rules, and that took very long. Also, vehicle dynamics, how are you going to do any control systems or any estimation if you don't understand how the car dynamics evolve? And also, you know, they found funny that some teams had springs, you know, because we have air springs in AMZ. Okay, in that moment we realized we had to do some session on basics of Formula Student. How does a Formula Student car look, and how are they normally done, and why do we do the stuff like we do it? And I think that was very cool because everyone learned a lot. Which is, after all, a bit of the goal of Formula Student. We made quite some mistakes this year. The first one came, so after everything we start developing, we have design freeze, and then we start having our first failures. We wanted to go to Formula Student Germany and Formula Student East, but we did not even classify for Formula Student East. So then you are working for the season, you assemble your team, and then you didn't prepare enough, or strategy was wrong for East, and we didn't get in. And we said, oh, maybe the waiting list. Also, we didn't get in after all. So you really have to work for this. This is as important as anything else, and as important as the competition is scrutineering, and as important as scrutineering is getting into the competition. The second, or the biggest failure that came after that was that we actually manufactured a new accumulator because of rules compliance and also to leave some space to the new computing system. And we didn't have this module leader structure that AMZ Electric has. We didn't have people from the car that built it, so we were really lacking expertise. And we made some mistakes while manufacturing the accumulator. We realized pretty late, like in April, that we could basically not use those cell stacks, and we could not use that accumulator. And that was also a very rough meeting, at least for me. I was not even in Zurich at that time, and some people, we just thought it was almost going to be the end of the season. We planned everything, and we realized that if everything went extremely fast, we would have like 2 or 3 weeks of testing with the real accumulator. That was quite of a bummer, but at the end, yeah, we worked pretty hard. We simplified the design to solve the mistakes, did everything as fast as we could. And at that moment when the software stack started getting, they realized that it was starting to be ready, but we won't have a car in the next 3 or 4 months. So we started developing the simulation way more, and Manish will talk about that because that was part of the success of it. And another failure was that we had a high voltage wiring system that was legal or was compliant in 2016, but not in 2018. And we changed some stuff, but then they returned the ESF, and then we changed some other stuff, and then they changed the ESF. And then we could have changed it from the beginning with like 4 or 5 days of work, but at the end we didn't. We just tried to solve it around that without changing it. And then 2 weeks or 3 weeks before Germany, we realized we were never going to pass scrutineering because they knew it, they were going to look for it. So we decided to go with 1 pair of high voltage wiring instead of 2, and that meant that we cut the power of Gotthard by half. That was also a very hard decision. At that moment, we did super simple numbers, and we realized that our fastest acceleration time ever would be like 4.5, 4.8 seconds, and we knew that other teams were way faster. So in order to pass scrutineering and to make sure that we will compete, we gave up half of our power, and we gave up acceleration, basically. That was pretty tough, I think. Some more remarks on testing. It's much harder even for driverless to have efficient testing than for electric or combustion. So you have to have a really clear plan in your head of what you want to test. It makes absolutely no sense to go testing something if it didn't work in simulation or in recorded data, because it's not like it worked once, you know. It has to work normally in a perfect world, and then it may work in a real car. But for sure, if it's not working in simulation without noise and in perfect, it's not gonna just work in the real car. Let's give it a try. That makes no sense. Also, the only way to detect mistakes is by visualizing them. So anything that is more complicated than 2 clicks is just too much. So you have to have the screens ready with different sorts of data, or actually online visualization. You should invest in that as soon as possible to be able to catch the mistakes as soon as you can. My last slide for this part. I think the relation with other teams is very important, or at least that's something it was interesting for us. With AMZ Electric, as I said, we didn't have alumni that much for this year. So we needed more help from them, or we asked for more stuff, and they are super nice people, so of course they helped us. But they were already at the limit with their own project, right? We will have to solve that somehow next year. So we are trying to help them with more our expertise, like software or controls, but they still give more to driverless than driverless gives back to electric. With other driverless teams, I think the atmosphere is amazing. Like, we actually get happy. We don't pretend. We get happy when the others do well, because we know how hard that is. We cheer for each other. And I think this atmosphere is super friendly and it's super nice. So I'm really proud, and I think it should continue like this, because it's not as competitive yet, and it's much more fun for everyone if we just get along nicely. One remark here was a bit of the misunderstanding of FSG track drive. So according to the rules, you cannot drive a trajectory that is based purely on upfront data. We interpreted that from the 2017 rules as you were allowed to do a track walk, so you cannot record differential GPS and then just follow it straight without looking at the track. So in the second track drive round, we actually used the previous track drive data, and we talked to the scrutineers, and they also saw that that was a legal move, but it was a bit of a misunderstanding, because other teams saw it differently. They didn't use the data when they could have, probably. And that created a bit of a rough situation. I hope it's all solved by now. And if we go back in time, we would for sure not do that, because we didn't know, or we never thought that it could be interpreted in the other way, right? We only loaded the map, like the cones, so we were using all the perception sensors and calculating the trajectory all the time, like 20 times a second. So yeah, it was unfortunate that we didn't see that on time, I guess. Now I'll give the word to Rafael, which will talk about the car and the actuators.
Yeah, thank you. I will just briefly introduce you to Gotthard, which is quite an amazing car, even without all the software. It's the 10th car in AMZ history, thus the big X over there. Yeah, let me just first start with the suspension system. It has a really cool and interesting suspension system. First of all, 1 spring per wheel, but not an ordinary spring, and as Miguel mentioned, an air spring with adaptive MRF dampers, and it also has a heave spring and a torsion bar acting as an anti-roll bar. The chassis, the mono, is a single-piece carbon fiber monocoque. As you can see in the rear, we have implemented directly in the mono a big rear diffuser. This came later was a real benefit for the driverless car, as Gotthard has a split accumulator into 2 separate parts. We have 1 battery behind the driver and 1 battery below the legs of the driver. As for aerodynamics, as I mentioned before, Gotthard uses a big diffuser This is due to that, or this enables a very efficient aero package, generating quite a lot of downforce without too much drag. Yeah, now to the batteries. I mentioned there was a split accumulator. This was before the changes made to the driverless car. We had a split accumulator, but then we replaced, or like for track drive, we're never going to use as much energy as we use for a electric endurance. So we removed the front battery below the legs of the drivers and made space for other components, like we placed the computer box there, which was quite convenient. And then we developed the own battery for the car, which also proved to be quite problematic in the end, but I think the design is very cool. Now then, let me talk more about the changes for the autonomous or the driverless car. The steering system is integrated below the car, directly at the tie rod. So it doesn't act compared to Fluida's system, which acted on the steering rack below the dashboard. It's below the chassis, and thus we're kind of bypassing the steering rack and potential flex or whatever play in the gears there. The system is quite cool. It's capable of turning lock to lock in half a second. In theory, practice a bit more, but still very fast. Then the next design or mechanical change, which was really cool, is the EBS system. This system basically works with a air spring or a air pressure tank, which acts on the brake and brakes all the time. This the EBS can be released with an oil system where we just pump oil into the cylinder in the rear. What's quite cool about this system is the lower and the upper oil compartment. They are connected through the hollow shaft in the middle, so that the redundancy is achieved by the two air valves in there. And now to close the circle on the modifications for the driverless system, Manish will shortly, or will later, talk a bit about the computer system and, of course, most interesting, software and these kind of things.
Thanks, Rafil. So today I'm going to present the software concept that we used in Gotthard. We will talk about the algorithms that we implemented and the conclusions that we derived from those implementations. In our opinion, this is the most important thing if you are building a driverless race car. So it defines the software architecture. This architecture represents the interaction between different modules. And if any of your package fails, this diagram will tell you what all package is gonna, or how your system gonna react with that. A neat and clean software architecture can save you from a lot of potential blow up. So at the top there, you see all our inputs. And on the bottom here, all the output of the software system. Input from the perception sensors, mono camera, stereo camera, and LiDAR goes to the cone detection algorithms, and input from the velocity sensor and inertial sensors goes to the velocity estimator. The output from cone detection and the velocity estimator goes to the mapping, are fused in a mapping and localization algorithm. To go for a full potential, we need to see 2 seconds in ahead. So if we want to full potential, I mean like if we want to drive at like 17 meter or 18 meter per second, we have to know 2 seconds ahead of us, which might not be possible because of the limitation from perception sensor, especially during the corners. So what we do is in the first lap, we go slow and we go in a discovery mode where we keep on exploring and we create a map. Once we have a map, then we switch to the race mode and we go with the full potential of the car. The mapping and localization algorithm will generate pose and map. So you know the map of the track and you know where you are on the track. That are used by the boundary estimation algorithm, and the boundary estimation algorithm will generate the boundaries, and which is kind of similar to generating a trajectory. So now from the boundary estimation algorithm, you have a trajectory and you know your pose, which are used by the control algorithm. With the entire software architecture, we are trying to mimic a human driver. So the output of the control algorithms will be the steering and throttle command, which goes to the low-level controls. And the low-level controls will actually decide how much torque has to be given to each of the motor using traction control and torque vectoring. Apart from this, the safety system code is also written on the ECU. For the entire software stack, we had 3 computing units on Gotthard. One of them was real-time ECU. Other 2 were used in master and slave configuration. Our master computer was PIP39 from MLP. It was rugged i7 quad-core processor from Intel. It was selected based on the trade-off between power and performance. We used, it has a GPU GTX 1050 to run our neural networks. And the slave computer was Jetson TX2. Why we selected Jetson TX2? Because it consumes very low power, around 15 watts if my figures are correct. And the slave and master computer are configured in such a way that even if the slave computer fails, the master computer will not get affected because of that. So yeah. Now talking about each of the module, first we will see our perception system. So input to the perception system is images from the camera and point clouds from LiDAR. Those goes to the cone detection algorithm, let's say cone detection for now. And the output of those algorithm is position estimate of the cone and the color probabilities of the cones. The goal of the perception system was, or let me just say that, one more point, that in actual, like the camera pipeline and the LiDAR pipeline were completely independent, which means that if the, in software and hardware both perspective, which means that if anything fails in the camera pipeline, still your LiDAR will be able to work and you can still do your mapping and localization. The aim of the perception pipeline was to perceive the environment accurately and for longer horizon. So all our sensors were selected in accordance with that. We had 3 cameras on the main roll hoop. 2 used in the stereo setup and 1 in the mono setup. Why did we do that? Because we want to perceive a longer horizon. So mono camera had a higher focal length, which makes sure that we are able to perceive the environment from 7 meters till 15 meters. And then the stereo stereo setup made sure that we are able to perceive the environment surrounding us and that too accurately. We used a 16-channel Velodyne high-resolution LiDAR. And as I said that these 2 are completely redundant system. So we had to come out with an algorithm so that we can view colors from the LiDAR. And really around 5 meters, like till the 5 meters, we can see the colors, and 12 meters, we were able to detect the cone from the LiDAR pipeline. So talking about the algorithm for the mono camera first. So we first detect the cones on an image. For that, we use a YOLO V2 network. And that network gives us the bounding boxes and the probabilities. Then we extracted the key points and passed through the key point network. This key point networks give us the points around the cones. Now we have the key points on the cone, and we know the 3D model of the cone. So we used a 2D, 3D correspondence algorithm, and then we get the position estimate using the mono camera. Here we have a video that shows the mono pipeline. On the top right, you see the YOLO network running, and on the top left, and on the bottom left, the key point network. You see at a few times it misses the YOLO miss few cones. And if the cone is not properly centered in the bounding box, the projection is also not that good. And on the right, it shows the position estimate. And somehow we find out that the variance is around 30 centimeter to 80 centimeter in the position estimate of the cone. Which is kind of fine, but if the variance is higher, then even the color information from the camera does not help you a lot, because then you don't know which cone it corresponds to, because the track could be as small as like 3 meters in length or width. Now coming to the that was the mono pipeline. Now coming to the stereo pipeline, it is an extension version of our mono pipeline. If let's say you have a stereo setup, how would you actually detect, how would you do the position estimate? Is you have two images, you will detect the cones or objects on both the images, and then you will project to find out the position estimate, or you will triangulate to find out the position estimate. So, but for that you need to run YOLO on both the images that you get from the stereo camera, and that is kind of computationally intensive. So for that, what we did was, so first it is like extension of mono pipeline, completely same. Now we propagated the bounding box from the left image to the right image. This made sure that we do not need to run another YOLO on the right image. So we propagated it, so that's a left image and this is the right image, and the bounding box corresponds to the same cone. From here we do a feature matching using SIFT, and then we triangulate to get the position estimate. Here we have a video which shows the stereo pipeline working, and the variance we got in the position here was around 30 centimeter, which is kind of decent given that it's not a depth sensor. But still we would like to try out some algorithm which could make it, which could improve it. Yeah, now coming to the LiDAR pipeline. So the input to the LiDAR is LiDAR point clouds. So what we first do is we trim to the interest of our area. The LiDAR point cloud will be huge. After that, we do the scan accumulation, and we compensate for the motion distortion of the LiDAR point cloud using velocity estimate. If we don't do that, we will see a distortion of like around 2 meters in the LiDAR point cloud. After that, we do a ground removal, which is, yeah, I have a figure for that. So we use an algorithm, a ground adaptive algorithm, which removes the ground from the LiDAR point cloud, but it creates a problem that it even takes out the points from the cones. Then you cannot actually identify whether it's a noise or it's a data point. So for that, we do a cone reconstruction. We make a cylinder, and we restore the point cloud corresponding to each of the cylinder, and we get something like this. Now, we are able to estimate the position of the cone up to the accuracy of near about 3 centimeter. After this, it was, yeah, so then, as I said, that LiDAR was used to even visualize the color or get the cone color probabilities. How did we do that? Was like this. So if you watch the cones, the yellow will correspond to the high intensity, and the black will correspond to low intensity, and yellow will be again high intensity. And it's completely reversed for the blue cone because the blue has white strip in the center. So now we exploited this property to identify the color from the cone, as the number of classes are just 2. So this method worked out pretty good. We trained a neural network on the gradient of those images, and yeah, that was used to identify the colors. So I have a video which shows the entire LiDAR pipeline. These are the row scans, and now we accumulated all the point clouds. We did ground removal, cone filtration, yeah. Now you will see the color estimation, and the accuracy for this was around 95% of color, like how accurately 95% was the accuracy of color prediction, which is quite good given that it is not a color sensor, it's a depth sensor. But still we had let's say in a given track drive you have like 200 cones, you will still face a problem that with the 95% accuracy there will be nearly 10 cones which will be misclassified. So that imposes a challenge on the boundary estimation to still generate the trajectory which can work out. Now coming to the estimation module. So from the top we had the cone position and the cone color probabilities, and now we want to generate a map and the pose using that information. So estimation module is basically of two parts: velocity estimation and mapping and localization. The goals for this module were you use quite a lot of sensors for the velocity estimation, so you want a redundancy against the failure of those sensors. And if a sensor fails, then, and you don't know about that, that can still screw up your, or that can still make your system fail, because most of these algorithms are recursive algorithms. So if you get a faulty sensor reading, it will keep on adding up, and which will be enough for your car to go out of the track. And the third part, or third goal, was to reduce the lap time. We want the estimation of the car pose and map to be really accurate even at high velocities. So yeah, this figure shows all the sensor setup that we used. So yeah, I would just focus on a single point here, that this year we went with a dual antenna GPS system. Why did we do that? Was because it can provide a really accurate heading even when the car is standstill, which is really good for the for a driverless car. And apart from that, it provides the measurement of the GPS velocities will be in 2 dimensions. Like it will give you velocity in the north and east direction, which is really useful because a single antenna GPS will give you just the absolute velocity. Yeah. And now we, what we did in the velocity estimation is we used an extended Kalman filter to fuse all the sensor data with a car model. And the output was longitudinal velocity, lateral velocity, and yaw rate. To detect the failure, we used 2 algorithms. One was drift detection and another was outlier detection based on the chi-square test. This represents the velocity estimation architecture. From this, I would just point out to a single point that we estimated the slip ratio along with the velocities. The advantage, like if let's say your car slips, maybe because of rain or maybe because of the high torque transfer on the ground, then you cannot use the wheel odometry to try to estimate your pose, because that's kind of like giving a false information to your filter. So we estimated slip ratio in the same filter, which makes sure that the velocities here are independent of the slip. And this worked out pretty good. I have few videos which shows the result. So that's on the top left is our, this is entire is our run at the second track drive in FSG, where one of our sensor failed. And you would know on the top left how the failure detection was able to identify it. And on the bottom right, this is a slip ratio estimation, and you will see that when the car hits a bump, then it will just record it as a slip and the velocity will not get affected. And on the bottom left, you will see the pure integration of velocity for the entire 310 meters, and you could see how accurate it is or how much it drift. The integration of velocity is compared with the GPS position, like absolute GPS position. Yeah, so this is a video. Now it will hit the bump, and the slip ratio will identify it as a slip, and the velocity does not get affected. And that was one of the sensor which failed, and it was purely rejected, and the absolute or the velocity of the car was not affected. Yeah, it will again repeat. Yeah. Now we have our velocities, and coming to the up the line, we want to find out the pose and map. For that, if I have to divide the entire 10 laps of mapping and entire 10 laps of the track drive, in the mapping and localization, the first lap is the discovery mode. As I said, we go slow and we try to explore the map. We use a FastLam algorithm for that. It is a particle-based approach towards simultaneous localization and mapping. After that, we do a post-processing, which I will tell later in the video. It is majorly calculating the boundaries of the map, and after that we do purely localization from the second lap onwards. So this is just the architecture of a SLAM, a simplified architecture. So here we receive the cone observation from our perception pipeline at 15 Hertz and velocities at 200 Hertz. We use velocities to do a delay compensation because the cone observation which you receive from any of the perception sensor till the time you can actually utilize has a significant delay. After that, it goes into the FastLAM algorithm. It fuses it, and then we do a post-processing. We calculate the track boundaries or select the particles. After that, we do again a post-delay compensation. That's because of the runtime of the SLAM algorithm, which will also cause a delay. And the output is map at 15 Hertz and the pose at 200 Hertz. Yeah, so I have a video which will explain the SLAM algorithm. Yeah. So here the black arrows shows the particle, and each particle represents a hypothesis. The best particle keeps on changing. That's why you see that the map is slightly flickering, because the best particle keeps on changing. Now, each of the particle is propagated using velocities, and then we do data association. In data association, like we receive a new cone observation. They are matched with the existing one in the map, and then there is an EKF update to do the map update. How well the new observation matches with the observation matches with the cone observation in the map will define your weights, and those weights are used to do resampling. You can see that the particles are spread quite a lot now, and there will be a resampling. In resampling, the fit particle will survive, and remaining everyone will die. And after the first lap, we compute the track boundaries and we switch to the localization. So this is pure localization. Yeah. We did a validation of our SLAM algorithm using a ground truth from Leica instrument. So what we noticed was the FastLAM 2 algorithm was giving us an accuracy of around 17 centimeter, and FastLAM 1 was around 27 centimeter. But the runtime of FastLAM 2 was like 1/3 of FastLAM 1. So that was what we find out. After that, now coming to the controls. Now we have a map, and we know where we are on the map. And so the next task is to find out the trajectory which the car has to follow and how to follow. So those things are done by the controls. And the goal of the control module is to take car to the limit. Now, going to the boundary estimation. When you have number of cones, like quite a lot of cones, then estimating boundary is not that trivial, because the perception range will be limited, and it's not necessary that every time you see the entire track in front of you. So how do we solve this problem, or how we attempt to solve this problem, is we discretize the entire space using Delaunay triangulation algorithm. And what that algorithm does, it maximizes the minimum angle of each triangle in the convex space, and that makes sure that all the triangles which are formed will be really nice shape. After this, we connect each of the edge of triangle to the other two edges. You can call them as branches. We will show that also in the video. Yeah, so these are branches, and the sequence of branches will be the path. Now the challenge is, how do we identify the correct path in this algorithm? So we define a cost function for that, and we penalize different cases. Like if, let's say, the left and the right side of the cones does not match with the blue and yellow, then we penalize it more. If there is a steep change in the track, then we penalize it more. So stuff like that, and then we try to identify the exact path. So with this algorithm, when given the correct cone probabilities or given the correct cone colors, it was working nice. But if you have misclassification, then it was not that good, or the car will probably go out. Yeah, so now we have a track, and in the first lap, we use a pure pursuit control to complete the entire lap. After that, we use a model predictive countering control. In this, we solve a optimization problem that defines a task, and the task is to complete the lap in minimum possible time. How do we do that? Is we maximize the progress along a given reference track using certain constraints. In our case, the reference track is the path middle, like is the track middle line, and the progress is the projection of the velocity along the reference track. And the constraints could be your vehicle model, and the tire forces should be in the friction ellipse. And one more constraint that we used was that the car should always remain in the track, and for that we implemented circular constraints. In our formulation of MPCC, we predicted, like it's model predictive control, right? So we predicted 40 steps ahead of us, and each step was of 0.05 seconds. That means that we predicted 2 seconds of trajectory in front of us at every time step, and we applied the control input of the first time step. We have a video that will show that. First, it shows the boundary estimation algorithm, where we are trying to predict the trajectory. And then after the first lap, when it switched to MPC, now. So the violet dots will is the trajectory, and these are 14 numbers. And at every time, we are predicting the trajectory for the 2 seconds. Now, the tools. So the entire software stack is done, but it is still incomplete if we don't say about the tools that we use to develop them. Most of these tools you would have already, or you would be using it. I would like to just talk about the automated testing system that was developed by AMZ last year. And like as Miguel said, that we had really less time for the testing. And so this was the tool that we think has saved us a lot of testing time, or have helped us to organize our testing better. So it consists of the 2 parts. It helps us in the continuous integration, and it provides a platform to visualize all our logs, which are ROSBAG in our case. Oh, fuck, sorry. Oh, sorry. So, yeah, ATS. So this video represents the continuous integration using the ATS. So whenever you commit a code and you create a pull request, in our case, the repository was Bitbucket. Bitbucket will include Jenkins as one of the approver, and you will get the notification on the Slack that your code is being tested. Jenkins will arrange all the simulations for you, and then you go to the ATS website. It is loading. So, yeah, so you go to the ATS website, and then you can identify which all test it passed or which all test it failed. And the best thing is you can run the entire it will run the entire software stack. Doesn't matter which part of the code you change, and it can run overnight. The simulations will generate some of the log or ROSBAG, and then those will get saved in the Dropbox or your server, which you can just play it again using the ROSBAG interface. Here you see all the commands, histograms, and plots, which makes debugging really easy, and it saves a lot of time. After this, so yeah, this is another, so as I said, there are 2 parts. The second part is visualizing the ROS data in it. So let's say you have a testing day, and what you generate out of that is hundreds of bags, and here you can visualize all the bags together. And the best part is it does not need any person to write a code or anything. You can just go on the website and you can play the ROSBAG. You can play the simulations, and you see all the signals and the frequency of those signals. So if you know at what point in the testing some of the things failed, you can identify easily what things failed. So the tools like this helped us in focusing all our time and energy towards the point where it is required, and that really saved us quite a lot of time. Yeah. And you can tag all the bags which are generated so that others do not, if that's a useless bag, then other people can identify. So putting all the software stack and tools together, what we achieved in the season was this thing. It was a post-season run, and it was a master thesis of one of our team member, Euro. And he implemented a learning-based model predictive controller on the car. So the car is learning from each of its previous lap, and you will see how it improves and it reduces the lap time, lap time in every lap. And it was like around 10% of the lap time reduction. This was using MPCC, and it is an ongoing research in the ETH Zurich, and all the code and everything for it is on GitHub, and it's open source. Now I will ask Miguel to put some concluding slides.
So I would just like to finish with a few slides. I think it's an awesome time to start or to do Formula Student driverless. The whole society is super excited about autonomous cars. There is not a fixed solution yet. Every team is approaching it from a different side, and it's all exciting, and we are learning from each other. It's not a mechanical only thing, or it's not a software only thing. It's a complete engineering challenge, and as we heard this morning, now we will all need it, apparently in the next 2 or 3 years, so yeah, better join now. I think it's super exciting and super encouraging how the whole software community developed in an open source fashion. For infrastructure, you get Linux, ROS, Git, all those things are for free just because people decided to share them instead of commercializing them. But not only that, you also have algorithms. So you have, as Manish said, MPCC, so the controller that we've based all our controller the last 2 years is now open sourced by the PhD that developed it. YOLO, you can detect cones by taking it from, again, just the darknet, put cones as training data, and you can start experimenting tomorrow. And I think we, as the software part of Formula Student, we should also be proud of this, and we should also promote it. So last year, we already started this GitHub page. That one has no content. It just links to all the Formula Student software resources. So I would here like to ask you to please join. Please put some data there to share. Put some algorithms, put some simulators. If you think about it, putting your own stuff for a very experienced team will help like 1 or 2%. But to new teams, it gives them everything, right? Because they don't know where to start, or they might be lost. And here they see a lot of examples, or they get data before having their car running. So I think it's pretty cool. This year, we are open sourcing our architecture. So as Manish said, we are very proud of those gray and red boxes. But it actually translates into code, right? So we took the whole ROS stack, we striped the algorithm so that we don't give the complete solution. But you know, if you have something better, if you have your own ideas, for sure, do it. But if you don't really know where to start, just grab this, and you can start filling the algorithms in their places without having to deal with the whole infrastructure, and then you improve it, you know? Like, it's just a starting point. This is how it looks, a bit the Git. So we already have like a data set from ours from last year, some SLAM algorithms, some control algorithms. Some guys from Edinburgh put some simulator there. There are links to the papers that have been published. So there are already two papers published about Fluella and Gotthard driverless. So take a look. There are tons of details there. And there is also any interesting video. You should also put it there because it's pretty cool. Some things that I would also like to remind. This is a slide from last year. This is still very true. Driverless Formula Student car is still a Formula Student car. This is not a software challenge. It's a complete engineering competition. And if you only recruit software, or if you focus on software, you won't make it. That I can tell you already. So focus a lot on the mechanical part and the electrical part, because the car either won't run, or you won't pass scrutineering. So you need a full Formula Student car, and on top of that, you need all the software. The fancy videos that we show are not what get us winning FSG. Those things happen once out of I don't know how many, and then you have an amazing video to show. But having something that works live there when you put it in FSG, that's what it's going to make you win. So don't focus on going fast as much as doing it 99 times out of 100. If you are lost, follow the pipeline, make it work first, then make it work more robust, and then make it work better. But going for a super fancy solution is quite likely to fail as well. And we told you how we suffered and how we put night shifts, and we had to do 2 accumulators and stuff. But we really enjoyed it. We were laughing whenever we were not crying. And we think it's an amazing experience. It's a super hard challenge, but of course you just have to take it and enjoy it. So one concluding video. Oh, there's no volume. Yeah, okay. It's funnier when you see. We are all laughing. This is post-season. But yeah, testing is fun. Being with guys that are as committed as you is quite fun. And developing such machines is something to be quite proud of, I think. So thank you very much. And we are welcoming any question that you have. Otherwise, just approach us later. So he asked if we are using a specific simulation environment. We are using Gazebo from ROS, and that's the one that we actually also use to run it on the server to generate all the nightly simulations. So we are purely based on Gazebo. We put our own physics script because Gazebo is not very good to simulate dynamics. But yeah, it's all Gazebo based. So the first year we had a very simple version. So we, from the beginning, implemented continuous integration on a server. So every time you commit to a testing branch, that is what we consider semi-stable, it would compile it. And that, if someone has done it before, someone from computer science, that should take a couple of weeks at most. Developing the whole ATS took 2 of our best guys a lot of months, or like 5 months or something, or 3 or 4. So you maybe don't have to go that extreme. Yeah, and they were also quite good, so I don't know how many of myself would take like 10 or 20 for a year. But it's something that is worth spending time on. So maybe if you don't get there, just have a middle point and then go next level up. The thing is, you have to have a tool to simulate everything. So in Italy, FS Italy, we realized our skid pad had a bug on the day before because we were looking at these things. If you compile, you cannot know. And then we realized we were working over the whole night and day, and then it passed in simulation, and then we passed and we actually run skid pad. So the question is if we ever thought about using end-to-end learning. We believe in models. We are a lot of control people that understand that the models actually represent the reality in a meaningful way. We, as you saw, we use learning, we use deep neural networks, but we think they belong to some places where you cannot do any better. So like computer vision or even LiDAR, those are just ad hoc solutions that can be learned. But as of now, we don't see ourselves using learning instead of control. So even the master thesis that was presented is learning on top of a model-based approach. So we just improve the model. I think end-to-end is going to be a nightmare to understand. If you just change any suspension setup, you have to retrain your model. If something doesn't work, You just have to retrain your model. And when you fail at FSG, you will retrain your model, I guess. So yeah, I'm not the biggest fan of end-to-end learning.
So thank you again for your really impressive presentation, and good luck to everybody for the next competition.